Okay, now I've been asked to do this in a Scottish accent, so we'll see how we go. The first part, you're not going to pay attention if I do it like this, though. So, it's going to be distracting. Anyway, corrosion, or more specifically, the prevention of corrosion costs Australian industries, homeowners and vehicle owners many millions of dollars a year. We know this. Okay, things rust, particularly in this area where you've got salt water coming in and affecting a lot of the structure, the infrastructure, because salt water can conduct electricity. And if you're conducting electricity, you are going to oxidize.
Is the swivel on?
I think it's having conniptions. I think if I move too quickly, it loses. There it is. It's got me there. So, the reason why we talk about corrosion as a redox reaction is because it happens all the time and it happens everywhere. If you can transfer electrons, which you can do if your ions are dissolved with charges, you can create that electrical current. You can speed up the process of corrosion, which is why saltwater towns, areas around the ocean have a lot of rust. And rust prevention is especially important when it comes to your boat. And, you know, if you're going out on the ocean all the time, you need to have some sort of galvanization or a sacrificial anode to prevent the rust. So, as we know, oxygen is the second most electronegative element and is present in our air, 20%. And it's also found dissolved in water. So metals have a low electronegativity. I've said that over and over again, and I'll say it again. And they tend to lose their electrons to the oxygen. The original definition of oxidation was to add oxygen to a substance. That's why we call them redox. Now, if anyone's reading this who's been away, I'm going extremely fast because it's a revision. Okay? We've covered this before. Gold is very unreactive. Gold won't react. Okay? It takes a very, very long time for gold to oxidize because it is stable and its electron configuration is stable. This makes it valuable for jewelry, of course, and due to its rarity, we use it as our basis for our currency. Okay? We have reserve gold, which is every piece of paper you have should have a gold equivalent somewhere in a bank or a fort. Okay? The idea that all money still comes down to gold. So, when we talk about rust, when we talk about the electrical reaction, iron in particular reacts with oxygen in a redox reaction. It forms ferric oxide, which is your rust. So, we've got our iron here. It's going to go into its ferrous ion state first. Then it's going to shave off 2 electrons. Come back here. You've got your ferrous ion, and it's going to lose another one as it gets to its stable state and become a ferric ion. A ferric ion, okay? Now, the request was to change my accent at every moment, so this is a 2-stage reaction. The overall reaction is, generally you'll see it written as the ferric reaction, giving off 3 electrons. So the reduction. Now this is more of a Latin-based, I don't know, I'm losing it. I'd rather just continue with the Scottish now that it's in my head. So, the reduction needs oxygen and water. You can't get rust without the water. So, you have this reduction reaction where you reduce water and you have the hydroxide ions. And the reduction occurs at what we call the cathodic site, or the cathodic site. It acts as a cathode. Remember, on your batteries, okay, reduction occurs at the cathode. You're not actually paying attention, are you?
No, I'm actually learning this.
Okay.
I'm not zoning out. It makes it more engaging. Yeah.
All right. Where were you like last year when I was... Anyway. So, where water collects, there's less oxygen. But what happened? What was I talking about? The cathodic side. That's right. What you get is the site where any reduction occurs doesn't necessarily need to be where the water is or where you've got your damaged iron. Okay? Because the iron actually conducts electricity, you can have a buildup of ferric oxide over here and the actual reaction, okay, occurring on this part of the nail or the steel beam or whatever you're using. So they flow out, these electrons are transferred as they're conductive, like a wire would conduct electricity, and it takes bits of the iron, reacts with the oxygen and the water, and you get rust. That is the main equation, okay? Now, at your anodic site, because you've got oxidation occurring, that's where you're going to get your ferric 3+ formed, and the hydroxide ions formed at the cathodic site is then going to combine with them to form iron hydroxide, which then turns into what we call hydrated iron oxide. So what happens, you've got this mix of ions coming together because of those reactions of the electrons going every which way, and because you've formed ferric ions and because you've formed hydroxide ions, they're going to combine, and then that's going to, some of these hydroxide ions are going to get together and form water because that's more stable. So then you end up with this ferric oxide with some water molecules bound in there, okay? And that is your rust. This is the orange color that's going to build up. Okay, so go over those reactions, check if your understanding in terms of what's actually happening with rust. You must know that it's a redox reaction, okay? If I'm going to assess you on your understanding, I'll probably give you the reaction and just ask you to balance it using half equations, okay? Rust will then absorb more water and then it will start flaking off, as we know. But the main thing we want to be concerned with, and that's just another diagram showing that. We don't really need to go into that one. Read on in your notes later on from DayMap. Now, what were the 3 methods of corrosion? Who can remember? Sorry, Talisha? Painting. Good. Sacrificial anode. So you get a more reactive metal. That's like if you put pastry and broccoli out on a buffet table, okay, everyone's going to go for the pastry. If you just have broccoli, everyone's going to eat the broccoli. So what that means is, if you've got a more reactive metal, oxygen's going to react more with the zinc, okay, rather than the iron, because it has a choice between the two, and one's more reactive. Move on to corrosion prevention. So, using an inert or unreactive coating, that's painting, that's putting plastic over the top, fiberglass or rubber on your cords. What else can you use? Yeah, mostly just painting or going over the top. So making sure that the water and the oxygen doesn't get in there and create rust, which is going to break it, okay? You'll notice that if you pick off a piece of paint or the unreactive coating in one area, you can actually get rust all throughout the structure. So that's why it makes this a very inefficient method of prevention. Using an inert or unreactive metal coating, okay? So you can actually galvanize with some metal over the top. For example, tin's a good example. Like most tin cans have the iron and then there's tin around it. As tin is less reactive than iron, it doesn't react with the contents of the can as well, which is often slightly acidic. If you've got tomatoes in a can, you've got an acid environment. So you want to be preventing that as well. However, you should never buy dented or damaged tin cans because it means the iron could be exposed underneath. So if you see a tin can in the supermarket, don't get it. Because chances are things might have gone off because there's chemical reactions now allowed to take place. Nickel, gold, and silver are often used as decorative coatings, mainly because they look nice. They're also very unreactive. So if you gild something, gild means you coat something in gold, it's unreactive, and it makes it look pretty. It's also a very cheap way to look rich. Less gold, and still I look, you know, nice and rich. But if you damage it, it's going to get oxygen in there. Yeah. You scratch it. You just take off the top and see. It flakes off rather easily. You just get a knife and... just about. Either, or you just cut it in half and see what's on the inside. But then you ruin what you've got. There's no point. No, not really. Because it's going to conduct electricity. Oh, I didn't even think of that. Yeah, you could weigh it and then see how many moles of gold you should have as compared to how many moles of iron you might have. That's a good idea. What's that? I didn't even think of that. It's genius. Although, really basic at the same time. Yeah, because if you weighed it and then you compared the molar masses, you should find that if it doesn't add up. In fact, density is another thing too. Iron's more dense than gold. So if your density's changed, and you can measure that by just putting it in a dense, like an overfill tube, and you can measure how much water comes out. And if that's not exact, then you probably got a little fake kind of ring from Bali. I'm not a racist, so no. I thought you wanted, yeah, I'm not going to do an Indian accent, that's just terrible.
Wait, are you Scottish?
What?
Are you Scottish? Why is it racist if it's... He's just laughing because he can't do it. Yeah.
Now, Lani, please, I'm trying to put this. I don't want to offend anyone, so let's go. I don't think that many times. Everyone just thinks I'm a clown. See, it's getting racist, and I don't like that. I've got to get into character, and I've got the Scottish stuck in my head. I suppose I can try to do some Italian, but I don't think it's going to work. Yeah. It's because it's stuck. Scottish is one of those accents, is once you have it, it doesn't leave. I'm not going to load this video on. This is turned into a travesty, but I'll see how we go. Anyway, now, what are we going to... I might skip ahead to using a sacrificial anode, okay? The sacrificial anode, that usually you coat your iron in zinc, you galvanize, you get an electrolytic cell, you do that reverse kind of non-spontaneous reaction to get the zinc coating the metal, and then what's going to happen is the oxygen is going to go straight for the zinc, and the water in that is going to react with the zinc and form, with the CO2 in the air as well, form a zinc carbonate, which is a white coating. So that's why quite often when you have new steel, it's usually galvanized. It's all shiny, but after a while it will get that white sort of finish. And that, you know, when you want to scratch the... You ever get that? When you see those tin things would have that coating on it? I don't know why, but I have this reflex to just scratch. I'm weird. Anyway, obviously that's just me. Also, if you've got zinc, if the iron is exposed, okay, it's not going to react because the zinc's still more reactive. It's still going to go for the zinc. So this protects it a bit further. And quite often boats have a large chunk of zinc in the water, and that prevents the rest of the hull from being oxidized. So the overall equation looks like this. Okay, if your iron ends up being oxidized accidentally, the zinc will take those electrons. The zinc will give up its electrons, and it will turn the iron back into its solid form. All right? So it just continually supplies it. It's like a medic for iron. Donates its electrons to the iron, thus sacrificing itself to ensure that the iron doesn't corrode. It's a noble metal. Yeah. You can also use electricity, okay, which some of you tried. When you've got your motor vehicles and you've got to coat them, you have to dip them in sulfuric acid. If you do that, metal reacts extremely fast with sulfuric acid. So to prevent the reaction, they hook it up to a small voltage. And as the electrons are supplied to the steel container, it is gaining rather than losing electrons. And so it doesn't corrode. Okay? So use electricity to do that. Okay, I want to talk now more about these electrochemical cells, which I think this is where we struggled the most. How much more time do I have? Probably 4 more minutes on this video. So right, again, all these slides are going to be on DayMap. And we have done these before. But just to show you, this is the voltaic cell. You have your anode. You've got your cathode. Okay, anode is where oxidation occurs. Cathode is where reduction occurs. Cathode is positive. Okay, if you have trouble remembering that, think of the little t in cathode. Think of the N for negative here. And angry ape is the other one. Okay, angry ape. The anode is negative in a galvanic or a voltaic cell. So, what's going to happen? Well, zinc's more reactive, so it's more willing to give up electrons. Goes along the wire. Goes to here, because copper is going to come out of its solution. This is copper sulfate. It's the electrolyte. Copper is going to come out of its solution, grab those electrons, and solidify. Okay? And you're going to constantly have this electric charge until the zinc is all gone and all the copper is solidified. Okay? You'll see a build-up over time. And you also need to complete and balance that charge with the salt bridge. Because if you have too many zinc 2 plus ions coming out into this solution, the electrons are going to start going back the other way. So in order to prevent that from happening, we pump chloride ions into here to react with the zinc. We put potassium ions down here to balance out the sulfate or any anion that's going to build up there as well. That's the purpose of the salt bridge, to keep allowing those electrons to not get attracted back to its original metal. So, what I would like you to do is draw this diagram, and then I would like you to label it. See if you can remember. The 2 half cells are aluminium and lead, and the salt bridge is potassium chloride. Write both half equations and the full equation. We're going to do that now. And then I'm going to just stop recording.